Hello everybody and welcome to yet again another video in our pre-calculus endeavor. This one is going to focus on exponential functions, and a few other video following this one will do the same. We need to spend some time on several topics here, starting with what is an exponential function. So what is an exponential function? Well, in the name exponential, you recognize the word exponent, right? So what is an exponential function? It's a function where the variable x is the exponent. So it's a function where the variable x is in the exponent place. In the exponent. Makes sense, right? Exponential, exponent, that's where the x is. For example, let's call this example 1 because we'll do a couple more. So example 1, perhaps the most typical would be f of x equals, I don't know, 2 to the x. I'm going to put the x in a different color to emphasize the fact that the x here is in fact in the exponent, right? So if the x is in the exponent, we are in the presence of an exponential function. All right, so let's see if we can actually sketch the graph of this. Its graph looks like, what does the graph of 2 to the x look like? Well, you know, the simplest possible way to sketch a graph is to take a table of values. So let's take a few points and let's see where that takes us. So minus 2, minus 1, 0, 1, 2. These are my favorite points. Sometimes it's not enough to sketch a graph of the function, but here I think it'll give us a pretty good idea. So minus 2 goes into this function. So that would be what? Minus 2 to the, no, I lied. That's 2 to the minus 2. Sorry about this. That's 2 to the power of minus 2. Here we go. I got it straight. So 2 to the minus 2 is what? It's, oh, those negative exponents, right? We remember we bring it down. So 1 over 2 to the 2, which is 1/4. All right, now minus 1. Replace the x with minus 1. So 2 to the minus 1. That looks like a weird symbol I made up. What is 2 to the minus 1? Again, negative exponent, bring it down. 1 over 2 to the 1, which is 1/2. Here's an easy one, 0. So 2 to the 0. Oh, well, anything to the 0 we know to be equal to what? Uno. Then 1. 2 to the 1, that's easy. 2 to the 1 is 2. And finally, 2 to the 2 is 4. So how does that pan out on a system of coordinates? It's going to look like this. So here's x, here's y. The scaling should actually be something like minus 1, minus 2, 1, and 2. And here 1, 2, 3, 4. And then 1 and 2 on the y-axis. So if we plug in the points that we have minus 2 comma 1/4. That's going to be very, very, very close to the x-axis. We have minus 1 comma 1/2. That's a little higher. We have 0 comma 1. we have 1 comma 2, and then we have 2 comma 4. So definitely not a straight line. So what does that look like? When I join the points, I will get something that looks like this. And that is typical of an exponential function. Starts very close to the x-axis on the left and then grows exponentially on the right side. So this is the graph of y, where do I put this? Y equals 2 to the power of x. A couple of things are interesting here to notice. First one, this curve right here gets really close to the x-axis, but never touches it. And what do we call a line towards which the graph gets closer to but never touches? We call this an asymptote. So here, the x-axis, also known as y is equal to 0, serves as an asymptote for this exponential function. So that's going to be my first remark. My first remark here, y equals to 0 is a horizontal asymptote. Again, if you're hearing the word asymptote for the first time, which I really doubt, but you never know, well, an asymptote is a straight line towards which the graph gets closer and closer and closer and closer without ever touching the line. So that's an important concept in graph sketching. It's also a very important concept in calculus. What else do we actually notice about this graph? Well, it has a y-intercept of 1. We can see that from the graph because the point 0, 1 was in our table of values. We could also take a look at the domain of this function, right? So the domain of this function, what is the domain? It's a set of x's that I can put into the function that actually works. So what are the x's that I can put in there? Can I put in some negatives? I did. I got a y value. Can I put in 0? I did. I got a y value. Can I put in positive values? I did. I got a y value. I can put anything that I want here, which is corroborated by the fact that if I do the vertical line test, see this vertical line will cross right here. This vertical line will cross. Wherever I draw a vertical line, it will always cross the graph of the function. What does that mean? It means that the domain is everything. The domain is R. Domain is all real numbers. If you wanted to take a look at the range, well, it's not something we do often, but while we're here, let's take a quick look. What's the range? Well, the domain is to the x, but the range is to the y. So basically, the range is the set of y values that are coming out of the function. And if you want to know this, well, instead of doing a vertical line test, you do a horizontal line test. So horizontal line, you're not going to touch the graph with any horizontal line when you are down here or even down there, or even the x-axis doesn't cross the graph. You start to strike the graph above the x-axis, so that means above 0. So the range would actually be from 0, and I'm going to exclude 0 because y is equal to 0 is an asymptote. The graph doesn't touch it, all the way down to infinity, and we never include infinity no matter what. All right, so that's a little intro to what a potential exponential function look like. There are a variety of other exponential functions. Let's take a look at some of them. All right, so more exponential functions. More exponential functions. Okay, so There's a variety of exponential functions that we can explore. Remember the one we already had? 2 to the x looks like the following. You know this, we just did it together. That's going to be y equals 2 to the x. Now, if you want to know, for example, what 2 to the minus x is, well, then you are going to get something like this. So this graph is y equals 2 to the minus x. Notice that they both actually meet right here. How do I know that this is the right graph for this function? I made a table of values, just like I did in the previous example. So you can replace x by minus 2 and minus 1 and 0 and 1 and 2, and you're going to get a curve like this. Notice that here the curve actually descends as you go to the right, as opposed to the blue curve 2 to the x, which ascends, which goes up, right? So basically they both have something in common. They both have the x-axis as an asymptote. Yes? Okay, we could also have something like this. So do I do this in yellow? I don't have a yellow, so I'll go blue and I'll go something like this. This graph is the mirror image of the blue graph over there, meaning that every single positive y became a negative y. What does that mean? Well, it's the minus of that function. So y is equal to minus 2 to the x is actually found right here. Notice again that the x-axis serves as an asymptote for this. And finally, we can have the same thing for the red curve. We could actually have the red curve to go like this, and that's the curve y is equal to minus 2 to the minus x. So it's the same thing as the red curve, but every positive y became a negative y. So that should actually meet, should be more precise in my graph, it should actually meet right where, right here at the point 0, minus 1. This is the point 0, minus 1 here. And this is the point 0, 1 over there. Ah, smudge! So 0 and 1 over there. So you have the garden variety of these functions. And of course, you can play a lot more with these if you basically add 1, subtract 1, and so on and so forth. So we could take a look perhaps at more exponential functions, perhaps in the following format. So let's take a look at, say, what is the graph of y equals, say, 2 to the x plus 1. So we know 2 to the x, right? The plus 1, what does it do to the graph of 2 to the x? Well, the plus 1 elevates the graph by 1 unit. So basically, we are going to get this. So instead of 2 to the x, okay, so I'm going to sketch 2 to the x here. That's 2 to the x, right? Now we have to elevate this by 1 unit. So by elevating this by 1 unit, I'm going to get something like this. Notice that the original horizontal asymptote, which was here, has now been moved to be over here. Right? So now, basically by doing the plus 1 to the 2 to the x, you have also moved the horizontal asymptote not to be y is equal to 0 anymore, but y is equal to 1. So we move it up like that, and then the y-intercept is basically now 2 instead of 1, because everything went up by 1 unit, right? So we can do the same thing for, say, what is the graph of y is equal to, I prepared something here, 2 to the minus x minus 1. 2 to the minus x minus 1. So how would I would sketch the graph of this? Well, I would certainly have a set of axes like this, x and y. Okay, so 2 to the x is this. What is 2 to the minus x? It's this one here. We'll do it in black. So 2 to the minus x is this function, right? But now I have to add minus 1, which means I have to subtract 1. So instead of having the horizontal asymptote at y is equal to 0, it's now going to have the horizontal asymptote 1 unit lower, like this, and the entire graph now goes down by 1 unit. So we get something like this. Getting closer and closer and closer to y is equal to minus 1. Yes? So notice that now the y-intercept is at 0. Why is that? Because if I replace x with 0, 2 to the minus 0, well, 2 to the 0 is 1, and 1 minus 1 is 0. So now it actually catches the origin. So you can actually do like different variety of these by playing with the plus and the minus. You can even do, well, let's do one last. You can even have something like, what is the graph of y equals 2 to the, let's say, 2x. Okay? So now you can actually play with the exponent if you want. That is going to be very, very, very similar to the graph of 2 to the x. The only thing here is that by doubling up the exponent, the rate of growth of the curve is going to be slightly faster. Okay? So, but technically speaking, the graph is not that different from the graph of 2 to the x. So here's again a set of axes, x and y, and the graph of this would very much look like this. It'd just be steeper for the following reason. Remember with 2 to the x, when x was 1, you had 2 to the 1, 2. Now, 2 to the 2x when x is 1, that's 2 to the 2, that's now 4. So the 0.14 instead of the 0.12 is now on the graph. And it's the same thing here for the 0.2. Now 2 times 2 is 4, 2 to the 4 is 16. So this is growing like way faster than the other one before, right? So it's basically telling you that the curve will get steeper faster if the exponent is increased by a factor of 2, like in this case. So you can play around with this and add and subtract numbers and so on and so forth. We are used to this type of manipulations. This is not unique to exponential functions, obviously. I just want to tell you about one very special exponential function in the domain of the social sciences. All right, so one very special exponential function. Very special, special exponential function. Now, some of you may have encountered this in high school. It's called e to the x. Notice it's exponential once again because the x is in the place of the exponent, clearly, right? So, and whenever x is in the place of the exponent, we have an exponential function. But now we're encountering this number called e, yes? So where e is actually a number that belongs to the same family as another famous number that you certainly have encountered in high school, pi. You know, remember pi 3.1415926, whatever. That's a number that has infinitely many decimals. That's not so remarkable. So many do. But these numbers never have a repeating sequence in those decimals after the decimal point. Well, that guy is a bit of the same thing. That's 2.7181 dot, 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 dot. It's on your calculator. If you want to know like more decimals of this, just enter e to the 1 on your calculator and it will actually show quite a few more decimals than the ones that I'm showing here. Now, the reason why we're studying this is because those exponential models with e are widespread in the field of social science. They're actually used to a variety of different occasions. For example, they are used to predict the rate of growth of virus and bacteria. This e to the x thing is also used to play around with stuff like radioactive decay and carbon dating. And the number of applications is really, really large. So basically, we're going to encounter this in what I'm going to do next in this video a little bit, and further on when we study logs towards the end of the semester. Good, so that's E now. All right. Okay, so let's talk about solving. So this is a new heading, solving exponential equations. Solving exponential equations. So how do I get the x value I'm looking for when I have an equation that has exponential functions in it, when x is the power? So we're going to start with like the simple case here, basically, and we're going to say the following. So what is the active principle here? What shall we rely on to solve these things? Active principle. Very simple, actually, very simple. If a to the x is equal to a to the y, so notice, if you have the same base but different exponents, it will follow, so arrow, it will follow what? What do you think? What does your gut tell you? A to the x equals a to the y. So if the base are the same and the two sides are the same, well, it must be that the exponents are the same, right? So it will follow that x will have to be equal to y. So what's going to be our strategy for this? What's going to be our strategy to solve those exponential functions? Pretty simple, actually. It will suffice to write all terms using the same base. So all the terms in the equation, try to write them with the same base, using the same base. I have just a bit of room here to do example 1. Solve, what shall I have? E to the x minus 4 equals 1. Ooh, that looks intimidating. Here's an e, and it's an exponential equation because x is in the exponent. All right, so my strategy is to write all terms using the same base. What is the base of this guy here? Well, the base is e, and the exponent is x minus 4, but the base is e. So if I am a little imaginative, maybe I can try to write 1 as something with a base e, so that the bases would be the same, so I can apply my principle that if the bases are the same, the exponents will be equal. So what can I do to 1 to write it as a base of e? Well, 1 is the same thing as e to the what? That's another way of saying it. E to the 0 would actually be the same as 1, because anything to the 0 is 1. Agreed? So basically, now that I have the same base, e and e on both sides, it'll follow that x minus 4 is equal to 0, because the exponent here shall be equal to the exponent there by virtue of our active principle. And that is very easy to solve. The answer is x equals 4. Wow, that was not hard. if you think of writing 1 as e to the 0, of course. That's really the essence of it. All right, so let's do some more equations where we have x in the power and we are trying to solve. Okay, so very dusty here. Let's get rid of some dust. Okay, exemple 2. Example 2. I have something here that I have prepared. 2.5 stars. 2.5 stars. So solve what? 3 to the x plus 1 equals 9 to the x over 3. All right. Once again, an exponential equation. Pourquoi? Well, the x, the variable, is an exponent, so it is here. So my strategy is what? Try to write everything using the same base. That's a 3, that's a 3, that's not a 3. I should actually write 9 as a base of 3. So I would say 3 to the x plus 1 is equal to, what's 9 as a base of 3? Isn't it 3 squared? Isn't it 3 squared? So 9 to the x is 3 squared to the x over 3. So 3 to the x plus 1 equals, let's apply some of the rules of exponents that we know. Exponents that are next to each other like this, what do we do with them? We multiply. That's 3 to the 2x over 3. Notice that the 3 downstairs is just a plain 3, meaning its exponent is 1, because I'm about to apply yet again another rule of exponent that says, well, if I have the same base and I have a division, then I can do what with my exponents? What do I do with the 2x and the 1? I subtract them. And look, that now becomes a to the something equals a to the something else. It's the same base. It's the 3 in both cases. So it follows that x plus 1, the exponent on the left, will be equal to 2x minus 1, the exponent on the right. Very easy to solve. Bring this over, so x is equal to, minus 1 goes on the other side, x is 2. And that is our final answer. It's not hard, right? Just a little bit of practice, and we're going to be very good at this. All right, let's try another one. Let's try another one. This would be example 3. What do I have for example 3? Same level, 2.5 stars. So solve, what do I have here? 2 to the 3x minus 2. 2 to the 3x minus 2 over 8 to the power of x over 2. All that is equal to 4 to the x plus 1. All right. Notice here, I have many different bases, don't I? Got a 2, got a 4, got an 8. I will be successful solving this, and so will you, if you can actually write everything with the same base. The smallest base is 2, so definitely I'm going to try to match that base of 2 with all the other terms. So, what do I get here? 2 to the 3x minus 2 over. We got to write 8 as something with a base of 2. What's 8? 2 times 2 is 4, times 2 is 8. 2 to the 3. 2 to the 3 is 8, but 8 is to the power of x over 2. All right, égal. That 4 won't do. I need a 2 in there. What's 4? It's 2 squared. So replace the 4 with 2 squared and start playing with your rules of exponents. So 2 to the 3x minus 2 divided by 2. Again, exponents that are next to each other we multiply. 3 times x over 2 is 3x over 2 equal to 2 times x plus 1 shall be 2x plus 2. Good. Here I have a division, so I have a subtraction of exponents. 2 to the 3x minus 2 minus 3x over 2. That is equal to 2 to the 2x plus 2. Let's go over here to continue. Let me catch my like terms. 3x minus 3x over 2 is positive 3x over 2. So 3x over, I'm sorry, I'm making a little bit of a mess here. That's 3x over 2. Why? Because that's 6x over 2 minus 3x over 2 is 3x over 2. Moins 2 minus 2 equals to the right side 2 to the 2x plus 2. And at this stage of the game, we have the same base. The 2 is the same on either side. So we're simply going to equate them. 3x over 2 minus 2 equals to 2x plus 2. So 2x minus 3x over 2 is equal to minus 2 minus 2. If I bring the minus 2 over, and this will be what? That's 4x over 2. So that's x over 2. And that minus 2 is minus 4. So cross multiplication, x equals minus 8, which is the answer to this equation. All right, so enough for today. We've done quite a bit. Next time we meet, we will actually look at also equations of that, but more like 3 stars and even 3.5 stars, but enough for one day. All right, so see you soon for the next one. Ciao.